Okay, so differential equations, exponential growth. This is a biggie on the test. They'll probably throw at least one free response question at you, in addition to some multiple choice. It tends to be a problem area, so that's why we're going to spend some time on it this week. So a differential equation, most of these problems will talk about, you got to write a differential equation when you have some rate, they'll tell you some rate of change in some quantity, pressure, population, a lot of different things, is directly proportional to how much of the quantity is present. So what you got to remember is back from Algebra 1, Algebra 2, Mrs. Gardner in geometry, directly proportional is y equals kx, and remember inversely proportional is y equals k over x. We won't see too much inversely proportional, but it's possible. So, but they'll usually do it in terms of this. Another thing you want to keep in mind, this differential equation, when they ask you to write a differential equation, this is one thing you got to notice, is that that variable and the variable with a k will be the same, and we're going to have to integrate this, and that's where the problem comes in. Not only is this a differential equation, this kind of differential equation is called a separable. If I spelled that right, differential equation, which means you can separate the variables. Okay, and it's pretty easy to separate, and in fact the whole process is very repetitive, and I'm going to show you how to do this once, and then I'm hoping you just know the shortcut. Okay, in fact that's what we want you to do, that's what we were counting on you doing, is learning the shortcut. So how do I integrate this kind of differential equation? Well, to separate the variables, I want to get the y's with the y's and the t's with the t's. Of course, I'm only seeing the dt, so that means what I'm going to do is I'm going to multiply both sides by dt, pretend this is a fraction for a minute, and then I'm going to divide by y, sorry. If I divide by y, that leaves me dy over y equals k dt. And then what we're going to do is we're going to think about this as 1 over y dy equals k times 1 dt. If we take the integral now, both sides, the antiderivative of 1 over y is ln y with absolute values. And I could write plus c here, but I'll do that just so we can talk through that, because I know some of you will ask that. And then the antiderivative of k times dt, well remember we can move that integral sign. We can move that here if it's a constant, and since there's a 1 there, we can just do this is k times t plus c. Now, I've got this c over here, and I've got this c over here, and they aren't necessarily the same number. If I were to subtract both c from both sides, this is still going to be some not constant, right? It might be 0, but it could be something else, right? So when we're doing these things, all we worry about is putting the c over here and call that good enough. Okay, now I want to have this like f of x in form f of x or y equals something. So in order to do that, I'm going to exponentiate both sides. That's the whole exponent. Well, e to the ln cancel out. If I just take the absolute value, I can just try to write it as y. Now here's the tricky part on this side. What you got to remember here, if I have a to the x times a to the y, I'm bound to determine to write y as a base. A to the y, isn't that a to the x plus y? Well, we can also write this backwards. We can pretend, if I've got a plus, I can write that as, if I'm adding those exponents, I can also choose this, multiplying those bases. And then e to the c is just some constant. And when we've been working with exponential growth before this year, you always just treated that as a. So that is the antiderivative of that original differential equation. So this is what's called the general solution to that differential equation. Okay, so when they ask you to write a differential equation, do I have that here? Nope, I don't. So I'm going to rewrite it down here. I had it on the other page, didn't I? So here's the differential equation. You're going to write dy dt equals ky, or p, or whatever variables they're talking about. Okay, remember the y and the y, that has to be the same. So that's the differential equation, and then the general solution's right there. Okay, so that's the differential equation they want you to write, and here's this general solution. I would love to have you be able to jump automatically to that. Use the right without having to go through that whole process. Okay, so now what we're going to do is we're going to solve some problems like this. Okay, so here's the first problem. They say to write a differential equation that states that fact. Well, here's a differential equation. They're telling me some extra information, and there's some not extra information. They're telling me some information in here. They're telling me that this is dp dt when the pressure is 35 pounds. So what I can do for this problem, I think this is the answer to that question, okay? But in order to use this other information, I can say that 0.28 equals some constant times 35 pounds, which this is kind of nice because if I divide both sides by that, I'm going to get, actually this should be negative, shouldn't it? Negative, because it's decreasing. That's going to give me negative 0.0008 if I did my arithmetic right earlier. Okay, so that's K. We'll hold on to that. Here's my solution. Here's my general, my differential equation. Now they want us to solve this differential equation. Well, if we just jump to that shortcut, I can say that pressure equals some initial value times e to the kt. So there's a general solution. Now we can also solve this a little better. We can get a more specific solution. We already know K from what they told us. We already know A because it starts at the full 35 pounds. So this differential equation is P of T, or P equals 35 times e to the negative 0.008 t. Okay, so there's a specific solution. Then they're asking us for part C. Well, 10 minutes later, this is in terms of 10, so we can just write 35 e to the negative 0.008 times 10. When I did this earlier, I came up with, let's see, let's turn the page. I got 32.31. I didn't write down 3 decimal places, pounds per square inch. PSI, I guess I don't need that slash, do I? PSI. Okay. Then they're telling me for this last one, now this is just pre-calculus kind of questions. They're asking me if it's 12 or greater. So 12 has to be greater than, we could just treat that like an equation. 35 e to the negative 0.008 t. Well, if you don't remember your algebra for this, we're going to divide both sides by 35. And then to get rid of unlock that exponent, I'm going to take the natural log of both sides. Natural log is important because I've got an e. And natural log and e are inverses. Then I'll divide both sides of this expression by negative 0.008. And when I did this earlier, I came up with Sorry, wrong problem. 133 minutes. Okay, so that's that example. Let's look at another one. So bacteria grows in the lab. Alright, so we get some germs growing. Right, the differential equation expresses this relationship. Directly proportional, that's important. So the bacteria in the lab grows in such a way the incidence rate of change is the number of bacteria present. So that could be B. So we can say dB dt equals KB. Now they want us to solve that differential equation for a function of time. This is the general solution. So we know from that work before, we can just write this as bacteria as a function of time is equal to some initial amount times e to the kt. So they're telling us that now for part C, there's 5 million bacteria initially. That's A. And 3 hours later, it's grown to 7 million. That'll let us find K. So we can say, in fact, let's just jump to that. We can say 7 million equals 5 million times e to the 3 times k. I hope you're following what I did there. I knew that 7, I knew that was 5, and I know t is 3 because it's 3 hours later. Alright, so if we walk through that same process as we just did, divide both sides by 5, take the natural log. So I'm going to get 7 over 5 equals e to the 3k. Take the natural log. 7 divided by 5 equals equals 3k. So the natural log of 7 divided by 5 divided by 3 is our k. I came up with 0.1122. Notice it's positive because this thing is growing. Okay, so now we want to write that equation. I'll squeeze that in down here. So the bacteria, the function of time, is 5e to the 0.1122 t. That would be that choice. What's this going to look like over 10 hours? It's an exponential growth equation, right? So we know it's going to look something like that. That's 5. It's going through the 5 billion mark. What will the back population be after a full day? Well, t is measured as in hours, so that's 24 hours. So 5e to the 0.1122 times 24. You crunch that, I came up with 73.864 million. Alright, when will it reach a billion? Well, this is just algebra again. A billion is 1,000 million. Alright, so divide both sides by 5. Take the natural log of both sides. So I divide that both sides of this by 0.1122. And you'll get the growth. You'll get the I got what, 26.700 hours. Okay, so a lot of this is pre-calculus. They're adding in this element of the differential equations. If you ever have to take a differential equation course, you'll just do a lot more. This is where you'll start. Okay, hope that helps.